It gives me great pleasure to introduce two fabulous graduate students from University of Washington. Got to know them a little bit over time. Dom spent 2 internships over here and haven't been able to get him out already. This will be a great talk on information visualization. They work with Jeff Hare over there, who for some of you might know, Jeff's been responsible for a lot of different innovations in graphics, including Prefuse and Flare, and then D3, and now the Vega series that they'll be talking about. They're going to be graduating in about a year and a half, so they'll be on the market. So this is actually nice to know. So, and as I said before, for those that were in here, they're going to be sticking around for a little while this afternoon, so we can set up some one-on-one talks. Send an email, and I can schedule that, or just come up and talk to me afterwards. Okay. So thanks very much, and take it away.
Cool, thank you. So before we begin our talk, I would like to advertise about our interval study on exploratory data analysis. So if you regularly perform exploratory data analysis in your work and want to contribute to your research, we are looking for people to participate in our studies. And this is the URL, bit.ly/uw-eda-study. And I think I'll ask you to forward the email to people. Yeah, cool. So today we are excited to present about Vega-Lite, a grammar of interactive graphics. In this talk, we'll show the design of the language and show how you can use it for your daily work. And since we have time, please feel free to ask questions anytime. To begin with, so we already have so many tools for creating visualization, and one of the most flexible class of tools provide languages for composing visualizations. The example of tools in this category include D3, Vega, and ggplot, and the language underlying tools like Tableau. Since there are already many tools, why do we need another language? So in this talk, we will first walk through what we like about these languages and see how Vega-Lite goes beyond these languages. To support an expressive range of graphics, many popular visualization tools adopt the idea from the Grammar of Graphics by Lee Wilkinson. The idea is that just like how grammar informs us how to compose words into sentences in English, a grammar for graphics provides primitive building blocks for composing an expressive range of charts. For visual encodings, these building blocks include data that we want to visualize, transform like filter, aggregation, and binning, graphical marks such as bar, point, area, line, the encoding mapping between data and property of these marks, and scales or functions that map data values from the abstract domains to visual values like pixels or colors. And finally, guides such as axes and legends that visualize these scale functions. With these building blocks, tools for customized visualization design such as D3 and Vega offer fine-grained control for composing interactive graphics. This kind of tool can be very expressive, but they require verbal specification and some technical expertise. For example, creating a bar chart in D3 requires at least a few dozen lines of codes and some level of expertise in JavaScript. In contrast, to support rapid exploration, both in terms of exploring data and exploring different visualization design, tools such as ggplot2 and Tableau allow more concise specification by omitting low-level details such as scale and guides. These tools then infer sensible default for these omitted properties and allow customization by letting user override default values. These tools with concise specification are flexible for rapid exploratory analysis. However, they can be limited for simplifying interactions. In designing Vega-Lite, our mission is to facilitate exploratory data analysis by providing an expressive yet concise language to simplify interactive multi-view graphics. Inspired by this previous language, Vega-Lite provides a concise language to express a broad range of visual encodings. In addition, Vega-Lite goes beyond this traditional grammar graphics by providing operators for composing multi-view graphics. We also present building blocks for composing interactions using selections. With Vega-Lite, all of these building blocks are available in a single unified language. So next part, Dom will first show you the design of Vega-Lite, and after showing the design, I will briefly show you how you can use Vega-Lite as a programming tool, and I'll let Dom show you the design.
Okay, thanks, Ham. So when we are creating visualizations, what we have to do is we have to create a visual representation of abstract data, and this helps us to amplify cognition. The main task of the visualization designer is then to define how abstract data should be encoded visually without having to worry about low-level details, such as scales or axes, or how to draw these. Take, for example, this weather data with information about the precipitation and wind and temperature in Seattle. This data doesn't have an inherent visual representation. Here, I created a table to show you the data, but inherently this data doesn't have a visual representation. So if the analyst decides that they want to look at a particular aspect, they can, for example, create a strip plot of the temperature. And this shows us what the temperature range is in Seattle. And in Vega-Lite, a single view like this one here is specified by encoding properties of marks, as Ham explained earlier in the, based on the grammar of graphics. So a strip plot is a visualization where we encode the value as the x position of the tick mark. And temperature here is a quantitative variable that shows a magnitude. So in our syntax, what we need to do is we need to specify the data source and then the mark that should represent the data. And most importantly, we have to define the mapping of data values to visual properties of that mark. And in our language, we express all of this in a declarative JSON language. And JSON is very easy to process with common programming languages and is native to the web, which is why we picked it. Behind the scenes, the Vega-Lite compiler reasons about the visualization and resolves ambiguity about low-level details, such as the scales and axes. And it does so with reasonable defaults, as you can see here. And omitting these details allows us to have a more concise specification. These defaults in Vega-Lite are designed to follow best practices in visualization design. But if the user wants to customize it, they can override them. So any of these properties that you see here, you can override, for example. So going back to the strip plot, it shows us the spread of the temperature in Seattle, which ranges from a couple negative degrees to around 36 degrees Celsius. However, it doesn't show us how many days have a particular temperature. So we don't know whether it's 1 or 10 or more days that have this 15 degrees Celsius here. In order to see that, we could create a histogram, which shows the number of records that fall into particular ranges. In other words, a histogram is a visualization of a distribution. So now the question is, how do we create this in Vega-Lite? Well, in the grammar of graphics, a histogram is a bar chart with the bar as the underlying mark. The x position is determined by a binned field, and the aggregated count maps to the length of the bars. So let's go back to the strip plot that we had earlier and transition to the histogram. First, we discretize the temperature data. Then, we encode the count, so an aggregate, as the y position of the tick mark. And this already looks kind of like the histogram. All we have to do is change the mark type to bar, and now we have the histogram. And yeah, so this is how you create a histogram for quantitative data in Vega-Lite. You could change the data to a bit different data set, and it would still work the same way. To make sense of histograms, Vega-Lite uses a binning algorithm which discretizes the quantitative data in human understandable intervals. Beyond that, Vega-Lite also determines sensible defaults to parameterize this binning. In the histogram, we bin the x-axis, which is a positional channel. Instead of showing an ordinal axis, Vega-Lite actually creates a quantitative axis as a guide. We know from the visualization literature dating back to Cleveland and McGill that the position is also highly discriminable. So we can use a large number of bins to show the temperature. If you instead use a non-positional channel, such as color, opacity, or shape, then Vega-Lite generates a legend with range labels, so rather than the axis as the guide. And it also uses fewer bins, because color is less discriminable. We have a harder time telling apart different colors. It's much easier for us to tell apart different positions. So having a grammar allows us to reason about the specification and optimize the visual output. With the grammar, we can incrementally customize the chart, as I've shown you. Another incremental customization is to add an encoding to an existing visualization. So for instance, we can encode the dominant weather type using the color. And then we get a histogram that shows us what the dominant weather days is for, the dominant weather is for days with a particular temperature. By default, Vega-Lite picks colors that don't necessarily resonate with what my feelings are about these weather types. So we can customize the scale, domain, and range so that drizzle is more gray, which is how I feel about drizzle. So when we added the color encoding, Vega-Lite automatically stacked the bars instead of layering them. And this is another example of these sensible defaults. If we were to, because of the stacking, the overall shape of the histogram is preserved. And this is what you can see here on the right. In this case, multiple things are interacting. To do this kind of reasoning, the Vega-Lite compiler took into account the channel, which was color, the mark type, which was bar, and a layout transform, which is the stacking. And these three components interacted in a non-trivial way to create a stacked chart that is more expressive than the bar chart with overlap. Just to show you that this overlap happens, if I change this to a line, you can see that these bars are in fact on top of each other. And so snow would be completely hidden behind these other bars. The stacked histogram more accurately shows us the data than the naive version would. However, it's still hard to compare particular bars here, for example, these two gray boxes here, because they don't share a common baseline. So instead, we could take this histogram with color. Instead of using color, we could lay out all of these bars in space. And so now we create one histogram for each weather type, and it makes it easier to compare the boxes here. And this is the first example of layered and multi-view composition in Vega-Lite. Vega-Lite has a grammar to compose views and makes them fit to new opportunities. And in our grammar, we have developed 4 basic operators. The first one you've already seen, the faceting, which we just used to lay out the histograms in space. And what it does is it partitions the data by an ordinal field and then creates a view for each of the partitions. Facet is the only operator where each view gets a subset of the data. In the other operators, each subview gets access to the full data. One of those other ones is the layering operator, where we can stack multiple views on top of each other. With the concatenation, we can combine arbitrary views and create complex multi-view displays. And repeat is a concise and data-driven way to concatenate views. And as a running example to go into details for these 4 operators, we'll use this histogram here that shows the monthly precipitation in Seattle. As you might know, Seattle is a beautiful place, but we try to scare tourists by claiming that it's raining all the time, which is of course not true, unless you're in November and December, which we are, right? Anyway, let's talk about this great chart. So in this chart, the x-axis encodes the date, which is grouped by month. And here we use the special operator, or this field time unit, which automatically puts all the days with the same month into one bin. The length of the bar encodes the mean or average precipitation of all the days that fall into a month. So with the layering operator, we can plot multiple views on top of each other. And this can be useful, for example, to annotate a chart. To use it, we first nest the specification under the layer keyword. And then we can add another view, or a second specification, to this list of views. And now the layer can show the mean precipitation with a rule mark. And note that in this case here, we only specified the Y location of this rule mark, so that we get an overall average for the whole year, not broken down by month. And Vega-Lite automatically makes these two layers share the X and the Y axis. In this case, only the Y axis, and the rule spans the full width of the chart. And this is another example of this kind of reasoning that goes on behind the scenes in the compiler. Another operator is the concat. And we can use it to take a single view, like the histogram that we had in the beginning, and visually concatenate it with another view. In Vega-Lite, you invoke this by just wrapping multiple single view specifications in an array, and then nest them under the concat keyword. Here we have the vconcat, which is for vertical concatenation. We also have hconcat for horizontal concatenation. And a recurring design pattern that we identified in these concatenated views is that we often have the same specification where just the field is different. Like in this case here, the only thing that changed is whether it's precipitation or temperature on the y-axis here. And because this is such a common operation, we promoted it to its own operator, and we call this the repeat. To use it, we start with a specification of a single view, and then nest the specification and add some parameters. First, we specify the list of fields that we want to repeat over, or that we want to create views for. And then we replace the field name with a reference to that repeated data. And so now we create one chart for precipitation, one chart for the temperature, and one chart for the wind.
I got a question.
Yes?
Can you change the aggregate first?
Not right now,
Okay.
but that's something to think about. Yeah. Right now we only let you do that for fields. Mm-hmm.
Is column here a keyword, or is this, could you call it foo?
Yeah, here it's a keyword because it automatically lays them out into a column. Yeah, if you call a row, it lays it out in a row. And we can actually take this a step further and do both at the same time. And this lets us create a view for each entry in the cross product of these two lists. And so that's why we can create this chart, which is a scatterplot matrix, or SPLOM for short. Of course, you could repeat arbitrary views, but here it was a scatterplot. And these SPLOMs are very useful to investigate relationships between multiple quantitative variables. And this can be, for example, as part of the dashboard.
You see histograms for those diagonal lines. Mm-hmm. Is there a way to do that in this, or
you would have to do concatenation in that case? Yeah, so you can use these SPLOMs as part of a dashboard. And some of them may even be composed in a dashboard. So as I said, dashboards can have multiple views, and they can be quite useful to make sense of larger amounts of data and the relationships between them. However, when you create these dashboards, you could, of course, create them in Vega-Lite. If you create every view separately, you would have to manually reason about the data management and how these charts fit together, or how they are laid out. And this is where the grammar aspect of composition comes into play. And to illustrate this, let's dissect this dashboard that's here on the left. So first, we have a bunch of single views. We have the histogram with the different colored bars, and the scatter plot, and the bar chart, or histogram, and the average line. And then what we do is we can use the facet, repeat, and layer to lay them out in space, combine, or annotate them into these composed views. And the cool thing is, in Vega-Lite, we can actually recombine these composed views again using the 4 basic operators. So for instance, we can take the 3 layered views on the right and create them in a data-driven way by repeating a layer. But this hierarchical composition that's going on here can continue. So we can combine the two repeated views with an horizontal concatenation, and then vertically concatenate that with the trellis view on the bottom. Mm-hmm.
Maybe I'm stuck. What's the difference between a repeat and a facet?
Facet is you define an ordinal field that you partition the data by. And repeat is just repeat the same view, and every view gets access to the full data.
Yeah.
Okay.
So when you have this facet down here, every view is for each weather type.
I see. Each of those is still temperature. Got it.
Okay. I understand your confusion here because they're very similar. You can think of it.
One's logically horizontally, one's logically vertically.
One is vertical, one is horizontal. So if you could transpose the data, you could use one operator. Here we have 2 because sometimes data just has a particular format. Mm-hmm. Okay, so So we created this whole view with a single specification. And because it is declarative, Vega-Lite can actually optimize the underlying data flow that's below this visualization. And in Vega-Lite, in the JSON format, this hierarchical composition is expressed as you would expect it. You can use a nested specification in place of any single view specification. Vega-Lite then automatically reasons about the data management, and how scales and axes should be combined. And these dashboards are a powerful way to look at multidimensional data. However, to really interrogate the data further, you want to interact with linked views and uncover hidden relationships. And let me show you how to do that in Vega-Lite. And this is where the interaction part comes in. So the basic building block for our grammar of interactions are these selections. And they are the core building blocks. Every selection defines 3 components. First, the first thing is the event processing, or how points that are in a selection are chosen interactively. For example, whether it should happen on a click or on a hover. Then the second thing is the points of interest, which might be the data tuples or visual elements. And then lastly, a predicate function to determine if a point lies within the selection or not. Well, let's make these selections a little bit more concrete. Let's start with a simple unit specification that shows a scatter plot for cars. So here the horsepower is on X, the miles per gallon on Y, and the points are colored by their manufacturing origin. The simplest definition of a selection consists of a name. Here it's called picked, and a type. And then we can use some conditional logic to change the color of the points based on what is clicked on. So how is this working? The selection type is driving a lot of the default values here for the selection. So the 3 components that I described to you earlier, they are all here, but some of them are in the defaults. So in particular, this single selection here is saying on click, select a single point, not on hover. And so, yeah, when you click them, they get added to the selection. We can change the type of the selection so that we can add multiple points to it. Now the default says on the first click, select the point, and with shift click we can toggle points in and out of the selection. And like with encodings, we can override these defaults. So for example, we can do, instead of on click, we can do it on mouse hover, and now we get this kind of brushing effect here. Okay, so besides the selections, we also introduce selection transforms. And they are analogous to the data transformations. They're a way to manipulate what it means to be in a selection. So let me show you how these work. Here is the single view specification from earlier. And as a data analyst, you might have a question of how does the number of cylinders of a car has to play into a trend that we're seeing here between horsepower and miles per gallon, this kind of negative correlation. And so to look at that, we can use the selection and add a projection transform. And this allows us to limit the selection to one field of the data. So now when we're clicking a particular point, all the points that have the same number of cylinders are highlighted as well. And with this interaction, I'm able to see that there's kind of 3 groups of cylinders. There's 8 at the bottom, 6 at the mid-range, and 4 at the top. But this sort of direct manipulation by clicking doesn't really give me a sense of how exhaustive I'm looking at these points. So there may be, I don't know, there may be cars with like 25 cylinders, and I wouldn't even be able to see them unless I explicitly click on them. So besides this sort of direct manipulation, we can invoke a transform and add some dynamic query widgets to the interactions that we've added. And now, which I guess is here. Oh, okay. So now we're binding this to an input element. And I can do the same clicking and interaction in this chart above, but we can also move the slider back and forth and see that there's cars with 3 and 5 cylinders, but only very fewer with 3 cylinders. So it's kind of hard to click on them if you're just using this. And because Vega-Lite is this declarative specification where most of the defaults or where defaults get filled in automatically, it is very easy to make small changes and rapidly generate and evaluate hypotheses in this over this data.
Question?
Mm-hmm.
So you're showing now introduction of some UI controls.
Mm-hmm.
Is there any support for theming and I can imagine getting this visualization into a larger application and then wanting to have those controls look like the other elements of control in my application?
Mm-hmm. So here, these are just standard HTML elements. This is just a standard range input element. So you can just CSS style them, yes. Okay, so here in this example, I've added just a few more lines of additional code so that we can look, in addition to just the effect of the number of cylinders, also the what the effect of year is on this. So now we have 2. And so perhaps luckily for us, we can see that as we're scrubbing on the year, that if we're going forward in time, cars are becoming more efficient. The timelines are moving up the scatter plot if we're moving forward in time here. Okay, so but all of these selections, transformations, and the selections are part of a grammar of interaction. And there's no templates or so whatsoever. And so these are reusable across a variety of different selection types, all of these components. So here, for example, is a continuous region selection, and it's called an interval. And now, by default, it allows me to select a region in both the x and the y dimension. And so we can create this brush. But I can go ahead and use this transform to restrict it to a single dimension. Here just the dimension that's used for x. And now we have a brush that only can only be moved over horsepower. And then we can also use a bind transform to bind the selection to the scale function rather than an input element. And so any guess what happens if we do that? Binding selection to scale. Well, this is what happens. We can now start to pan and zoom in the scatter plot. And this might feel a little bit magical, but let me unpack what's happening under the hood here. what's happening is that we're establishing a two-way binding between the selection and the scales. So the selection is populated by the scale domains, and then the scale domains themselves are being driven by the selection. And so this is what gives us this, panning and zooming. So yeah, there's this two-way binding, and then this reverse population. And as you can see, there's implicitly, Vega-Lite creates this, this binding here, but you don't have to manually do this. But you could, of course, override it or put it into different parts of a specification. So all of this is the interaction. All the interactions that I've shown you so far have been restricted to one single view. But the reason why we designed multi-view operators and the grammar of interaction is because these interaction techniques are most effective when we're coordinating multiple distinct visualizations. And so I can use a repeat operator to go from a single scatterplot, like the one I've seen before, to a matrix of scatterplots. And now we can start brushing and linking between all of them. And automatically, all of the selections work in these four subviews. And with these sorts of selections and transformations, a whole number of other custom techniques fall out very naturally. I can set up an overview plus detail for focus plus context interaction. Let me show you what this might look like. So we start with just an area chart. We have the same area chart again, just with slightly taller. And then we're adding we can add a selection to the upper chart. In this case, it's an interval selection restricted to X, so we get the brush. And then we can use that same selection to change the scale domain of the second chart. And then we get this overview and detail focus and text visualization. And this is similar to the other example where I said some magic happened. Here in this case, we split where the selection is used and where the selection is defined into two separate views. Mm-hmm.
Is the word region here a keyword, or is it arbitrary text?
It's arbitrary text. This is the name of your selection. You can define multiple selections here if you wanted to. OK, so as a final example of what we can do with these interactions and the grammar of interactions, let me walk you through how to create a variant of cross-filtering. Cross-filtering, of course, being a very popular visualization technique. So we would start with a histogram, and here in this case, it's flight data. So this is a histogram that shows us for the binned hour how many flights are taking off at that time. Then we might repeat the same chart to look at different variables. So besides hour, also the delay and the distance that how far the flight was. And so we just replace the field with a reference to the column. And now, what we want to do is have this some kind of layered interaction here. So first, we add a second layer, which is just the same as above, but we change the color to be this kind of gold. And now we have 2 times the same charts on top of each other. So let me just focus a little bit and collapse this down. So now we can add a selection to the chart, which is again just restricted to X. So we have the brush. Now we can start brushing in these charts, but nothing happens so far. But we can use the selection then to filter the data in the other chart, in the one with the golden bars. And so now what we get is this cross-filtering interaction where the golden bars in the other charts correspond to the data that is selected by the brush. And this is all you need to get cross-filtering working in Vega-Lite. The cool thing is what we're talking about here is 35 lines of JSON in a very composable manner. So we might be able to just extend this to add another chart that we can interact with. OK, so now that you've seen our language design and kind of what thoughts went into the creation of this grammar of interactive graphics, Helm will show you how you can use Vega-Lite and what we've built on top of it.
Cool. So first, let's see how you can use Vega-Lite as a programming toolkit. So to use Vega-Lite, we provide a compiler that translates a Vega-Lite specification into a low-level specification that we also develop at UW. You can then use Vega's runtime and create a visualization both natively on the web or via server and render visualization using either Canvas or SVG. And because we use the underlying Vega architecture, we also support streaming data as well. And by using a declarative JSON syntax, Vega-Lite can serve as a file format for authoring and sharing visualization and provide binding support for different languages. For example, to perform analysis in Python, you can use a library called Altair, which is developed by Brian Granger and Jake Vanderplas. With Altair, we can create a histogram that we have built earlier in Vega-Lite using a native Python API that maps directly to our Vega-Lite syntax. This can be convenient if you perform data analysis in Python. And we would like to also highlight that Altair's API is automatically generated from Vega-Lite's JSON schema. This means that when we publish a minor version, the Altair team mostly need to just run that script to update their API. And this approach is not limited to just Python. There are other projects that try to wrap Vega-Lite in other languages as well. In a recent article by Dan Saber, which compared different Python data visualization libraries, Dan concludes that it's the one-to-one-to-one mapping between thinking, code, and visualization that's his favorite thing about Altair, and of course, the underlying Vega-Lite language design. And the Altair team themselves are also very excited about our design and mentioned that they see Vega and Vega-Lite as perhaps the best existing candidates for principal lingua franca of data visualization. And just a few weeks ago, we were excited that Jupyter Lab, which is the next generation of the popular Jupyter Notebook, would ship Vega and Vega-Lite by default. In addition to use Vega-Lite directly and via wrapper APIs, Vega-Lite can also enable higher level tools like graphical user interface application that can let user create Vega-Lite plots via UI without writing code directly. And we can even use Vega-Lite as a representation for visualization recommendation. To give an example of a tool that does both of this, we would like to show you Voyager, a visualization tool that augments manual visualization specification with recommendation. And the goal for this tool is to promote breadth in exploratory analysis and reduce tedium for manually specifying charts. And to support this goal, Voyager uses Vega-Lite to both specify and use Vega-Lite as a model to recommend visualization. Here's the Voyager interface. And here we are showing a dataset about cards. And with Voyager, it's a single unified tool that allows users to both specify visualization and also show recommendation to user. After loading the dataset without having to create any views manually, we first show Univariate summaries so that user can browse different charts and see that, see summary of different data fields. For example, here you can see that in this dataset, a lot of cars have even number of cylinders, and only some type of car have odd number of cylinders. You can also see that this dataset is quite old. It's from 1970 to 80 something, older than me at least. And user can also use the drag and drop interface to build a specific view, similar to tools like Tableau. For example, dragging horsepower to the X shelf would create a visualization that shows a zip plot of horsepower. And under the hood, Voyager use Vega-Lite, create Vega-Lite specification that map horsepower to the X channel and use Vega-Lite to render the visualization. Based on the specified view, Voyager also suggests different types of related views to help analysts discover relevant variables and alternative ways to summarize or encode the data. For example, up here, we recommend related summary views. And to do so, Voyager consider the Vega-Lite specification of the dot plot above and determine if we can calculate summary views by applying aggregation or binning. And here we see a plot that shows histogram of horsepower and a plot that shows mean of horsepower. It can similarly suggest other kind of plots, for example, suggesting a plots that show horsepower with other additional variable like horsepower and acceleration, horsepower and displacement, or horsepower and miles per gallon. And to give user more control to create a collection of views manually, Voyager also provide a wildcard to specify a varying properties of the visualization collection. For example, on the left, we have wildcards for varying multiple fields. If I drag a quantitative fields wildcard to Y, we then create a gallery of scatterplots showing horsepower with all other quantitative variables. Under the hood, we also use Vega-Lite to enumerate visualization for both related views and wildcard. And in this case, for wildcard, we basically enumerate different quantitative fields for the Y channel. With all these different interaction methods, analysts can rapidly explore different aspects of the dataset and create specific visualization to address their specific goals. And to recap again, whenever user specify things manually, Voyager create a Vega-Lite specification and render the plot, and also analyze the intent that user provide from the visual interface and provide it with further recommendation. For more details about different kind of recommendation and wildcard specifications, as well as the underlying query language that we build on top of Vega-Lite called CompassQL, you can look at our research paper. And I'm also happy to come to give another talk about Voyager in detail if you're interested. So from Voyager, we can see that Vega-Lite can be used to support recommendations of data and visual encodings. One area of future work that we are excited about is applying similar approach to recommend interactions. With Vega-Lite's concise syntax for composing interaction, we can just add one small targeted changes to a specification and generate a dramatically different interaction technique. With these small changes, we can easily write a program to enumerate the space of interaction design for visualization and recommend interaction techniques as well. To summarize, in this talk, we have shown you the design of Vega-Lite, which include building blocks for specifying single views and compose them into interactive multi-view graphics. We have also shown that Vega-Lite can be used directly as a programming tool, both directly on the web and via other wrappers such as Altair. And in addition, Vega-Lite can enable graphical user interface as well as recommendation in a system like Voyager. And we are happy to announce that last Tuesday, we released the first production version of Vega-Lite 2, which include all the composition and interaction features we described in this talk. And we also have tutorials and documentations online at vega.github.io/Vega-Lite. And if you're interested, you can start playing with Vega-Lite using our online editor without the need to install anything. We also provide auto completion and some hints for documentation on the editor. And finally, we would like to thank contributors to Vega-Lite and related projects. Of course, not just to us or Jeff and Arvin who co-authored the paper contribute to this project. Many people contribute to Vega-Lite, Altair, and Voyager. And yeah, so here are the top contributors. And with that, we are happy to take questions. And if we also can demo the online Vega editor if you want to.
Great talk. I'm wondering what is the computation engine underneath, especially when you're dealing with big data. So do you support some kind of sampling to be able to quickly produce some visualization or some iterative approach to refining the visualization?
So we don't do that inside Vega and Vega-Lite directly, but because there are many ways to bind data to Vega-Lite. You can use URL or you can bind data at runtime, which means that the applications that you write can do some sampling before they pass the data to Vega or Vega-Lite.
And I think one of the next steps for us is also working on or taking the declarative specifications and reason more about what is happening exactly. I think now that we have not just the visualization, but also all the interactions in a declarative way, we can actually reason about where data has to be and what data we have to update when users start interacting with the chart. So we think this can be a step to really have interactive applications over large data, which also actually happens to be kind of my research area. So.
Yeah, and for applications like Voyager, where multiple Vega-Lite plots are displayed, the fact that Vega-Lite is declarative, one thing that we are planning to do is try to analyze common data flow for different plots and reduce the redundancy when you calculate aggregation and other transform for different plots as well.
Yeah, the other thing is just using aggregation, and actually Daniel and I worked this summer on different aggregation techniques for visualization, and we actually used Vega and Vega-Lite for the rendering part for that.
I have one more question. So the idea of direct manipulation is actually very fascinating, and I wonder, is it possible to get to the extreme end where you can pretty much create any kind of grammar just by interacting on the canvas without having to type anything?
So that's more about how you would create these kinds of visualizations, or the specification for the visuals? Yeah.
Yeah. So one of the reasons that we develop Vega-Lite is to develop applications like Voyager. So by having a model that can use as representation, then you can build any kind of UI. You can build other UI that do things similar to Voyager, but work in different way, or maybe on tablet or whatever. So the answer is yes, but yeah, you obviously have to spend time to develop the UI.
One example is the Lyra tool, which is a tool that Arvind developed, which lets you, with a drag and drop interface, create Vega specifications. He's now a faculty at MIT and wants to.
He will be in.
Or he will be in the fall.
In fall. Yeah.
He's looking at.
What is the name of the tool?
Arvind.
Lyra.
Or Lyra, yeah.
Wasn't Lyra originally developed on top of D3, and then later?
On Vega 1.
Oh, it's Vega 1.
Then Arvind did Vega 2, which Vega-Lite 1 was based on. Now Vega-Lite 2 is out, which is based on Vega 3. Yeah. And actually, Arvind started updating Lyra to also use some of the automatic recommendations of the smart defaults from Vega-Lite. So the new version of Lyra is actually using Vega-Lite and Vega. But what Arvind is interested in is also looking at how you can create interactions by demonstrating them in a UI. This was a lot of things, but Yes, Dan.
When you're developing a language like Vega-Lite, you picked a couple of core operations, the facet and the repeat and that sort of thing, and a couple of fundamental mark types, the bar and the rect and the circle. How secure are you that you've got them all, for some definition of them all? Or alternately, is there a shape to the space that you've got, or is it that you had a handful of demos and you decided you'd build a language that was good enough to hit all those demos?
That's a great question. And we're not claiming that we cover them all, especially for things like Vega-Lite, which we aim more for statistical graphics. So we don't support like bubble pack layout, for example, and probably wouldn't support that. At the Vega level, which is another tool that's lower level, then there are more support for those kind of things. So yeah, we don't claim to support all of that. What we try to do is try to aim for what's more frequently used things. So
the story behind Vega-Lite is that the first version was actually created to build Voyager 1. That was the original reason why we even wanted this language. And then there was a paragraph in the paper. And then we noticed, this is actually something that could be useful beyond just Voyager 1. So then we made it its own library and added interactions and compositions and all of these things.
Yeah, and we see feature requests and even better pull requests all the time too. So
So ggplot tends to be used for a lot of people using R to generate end, visualizations that incorporate in papers. That means they start styling and a couple of other things, sort of a little bit easier than actually manipulating CSS and SVG things. Is that something that you guys are going to look at, or have some? Part of this is sort of, once you got this, how much can people sort of add to it?
Yeah, we actually already have that in Vega. Vega has different renderers, not just to SVG but also to Canvas, and that's why normal CSS rules don't apply.
Right.
But what you can do is you can apply, or you can set these, what are they called? Not styles, but
config.
in the config you can define how certain elements should be, what are the default colors should be, what the margins should be, and so on.
Yeah. So the answer is there are a lot of ways to customize plot. Even though what we show in the talk is mostly the concise syntax, most of the things in Vega-Lite can be customizable. And even for things that you cannot customize directly in Vega-Lite, because we compile things into lower level Vega specification, if you find a rare use case that we haven't implemented them in Vega-Lite yet, you can use the Vega output and customize them too. And we also have theming system to enforce that all the axes or the bar mark should have 13 color. For this kind of thing, you can create theme using Vega-Lite and Vega as well.
How many other people have built renderers for Vega? Is it just you guys?
So there were some people who built a prototype for WebGL.
Yeah.
And then MapD uses Vega for as their format between the front end and the back end, and they're thinking about also building new renderers.
Yeah. But I think for the most part, I think the biggest one that need someone to do would be WebGL. But for normal usage, we don't have that big data. SVG and Canvas pretty much like cover.
I think that's one really exciting part about Vega and Vega-Lite. It's just this ecosystem of tools, and having one specification language that different tools can generate, and then different tools that can interpret this language or reason about different parts of that language, automatically optimize parts, render it with different tools. You can go from Vega-Lite to Vega if you need the customization, as Ham mentioned. You can then use Vega and Vega-Lite more or less as data exchange formats,
right.
Which is also one of the core design principles behind Vega.
Yeah, and we know that, for example, Wikipedia already support Vega because the fact that it's declarative, so you can easily add it to Wiki. And now that we release Vega-Lite 2, they are interested in having Vega-Lite as part of Wikipedia as well.
Yeah, for them it was crucial that it wasn't general JavaScript, because they don't want people to run arbitrary JavaScript on other people's computers for obvious reasons. And so their declarative format was the perfect way to express this. And we also hope that this could be applied to other things like publications, maybe, where instead of you having to embed a figure that's just an image, it could be an interactive visualization, which comes with your paper.
Yeah, and we do use Vega-Lite for our papers too. So yeah.
Unfortunately, they're not interactive in the PDF anymore.
So is there an extensibility model for the language, and how is the language defined? I guess switch the order of those questions.
So the language is defined by having a set of primitives, and this primitive interact with each other. So in a way, adding things need to be a little. When we add new things, we have to be a little careful, because it's not just like add one thing that's standalone. Like if you want to add a new D3 library, you can just add anything, because your user for D3 would write things up manually. But for Vega-Lite, because this primitive would automatically interact with other things, then it needs some careful consideration when you add things. For extensible part, one thing that we are adding is having ability to have macro. Like, for example, if you think about statistical graphic like box plot basically have the box part, which is basically a rectangle. Then you have the line, which are the whisker. So having ability to add macro for even more concise syntax is one thing that we plan. We already have support.
maybe if your question was specifically about how the language is defined. So right now it is defined by what we write down in our documentation and by the implementation. But we actually also generate a JSON schema which says exactly what are allowed properties for the language. So they describe the whole space. But they obviously only describe the syntax, not so much the semantics of things.
Yeah, and for JSON schema, if you start playing with the Vega editor online, then if you type something that's invalid, it will warn and validate.
Yeah.
Yeah.
So have you thought about adding some kind of animation components to this, or do people do animations with visualizations?
Yeah. So we right now for both Vega 3 and Vega-Lite 2 don't have animation inside our language, but what you can do is if you use SVG, you can already apply CSS animations already. We do plan to add animation first to Vega 3 and then later to Vega-Lite, but not in the next few months. Yeah.
And more generally in the academic community, are you aware of some recent work in the space of grammar for animations, not necessarily with data visualizations, but general grammar for animations or PowerPoint animations?
I don't know if there's research-specific work, but for declarative animation, like for example, D3 sort of try to embed animation transition into domain-specific language. CSS transition is sort of similar in a way, so yeah, I guess those are the two that I know of. And as I said, CSS transition can be applied to Vega-Lite plot as well if you use SVG. And when you say, for example, when you have a streaming data and you keep updating a plot and you want to transition the plot, then you can use CSS transition.
But there will also be interesting to, again, reason about the specification and having some kind of grammar aspect to animations, so that an animation is, by default, somehow meaningful. But I think that requires some more thinking to actually make it fully work.
I was going to hammer on the first question a little bit more, is that if you were to drop this into a server client model where the server is doing the computation, how would you break up Vega so that, because you have like specification, but you want to break it out so that somehow it generates, ideally, not biased at all by Power BI, generates some sort of data view that it wants, gets it back, then does its thing. How would you kind of handle that?
So Vega is fully reactive. It's a fully reactive system. There's an API for adding data to it, updating or removing tuples from the data, and then it automatically only updates the parts of the visualization that need to be updated. But if you're taking your Vega-Lite specification, generating the Vega from it, it kind of expects that all the data is there. So if you want to push some of the computation down, you would have to split up that data flow and have some part on the server, some part on the client. So that's about interactive parts. But
I guess the obvious next question is like database community. Is there like a common data format that I could compile my request into that any kind of like backend server could manage and then give you back that data that you wanted?
Are you talking purely about static visualizations now? Because if you have interactive visualizations, then an interaction could affect some part of the data, right? And then you would have to rerun the query on interaction and update. I actually wrote a paper about this, which I guess I should send you.
At the workshop?
At the DSIA workshop,
Yeah.
2013, 14.
Okay, never mind. This is specific.
So there in that paper we talked about this idea of taking a declarative specification and reason about the data flow behind it and automatically split it up and dynamically change where certain operations are taking place. But that was before we even had a declarative format of interactions and visualizations. Now we have that. So I think now we can actually go and get to that vision and do what you and I want to do.
Yeah. So basically, to sort of answer your question a little bit more, given a Vega-Lite specification, you can write a program that decouples just the data flow part, and then you can execute that data flow part on the server. But the tricky part will come when you have interaction. So you should only decouple the part that doesn't involve interaction. Otherwise, it's going to be a lot of code involved.
Yeah.
But just if you only want to extract the transform part that do before you do instruction, you can extract that to the server. And for Vega, there's a dataflow API that you can run the dataflow of Vega without caring about visual encoding at all.
Or it can be a bit more nuanced, something in between those two approaches where you send some data to the client that allows for some limited set of interactions. For example, for the cross-filtering, you could send a data cube to the client, but probably not the whole data cube because it's too large, so maybe you restrict it to certain dimensions of the data cube. Yeah. Other questions around that?
In Voyager, you showed the wildcards. Is that Vega reasoning and doing its own type discovery, or is there some expectation that there's some schema associated with the data set?
Yeah, so in Voyager, then we given the input data, we'll analyze the schema and allow user to classify the schema. And the question mark wildcard thing is actually a part of another language that we build on top of Vega-Lite. We don't have time to describe much about it, but basically that's another. So that's Vega at the low level. That's Vega-Lite that compiles to Vega. Both Vega and Vega-Lite describe a single visualization, right? But then there's another level of language that describe a collection of visualization and allow you to sort of group things and sorting based on ranking, like perceptual effectiveness ranking. So wildcard is at the level on top of Vega-Lite.
Or in Alex terms.
Specific to Voyager?
So it was designed for Voyager, but you can use it to build other applications.
And are you thinking of releasing that as a standalone thing, or is it you just kind of go lift from Voyager right now?
So the thing is called CompassUL. It's on different GitHub repo. I know a few colleagues in research that try to use it for other purposes already. For example, I don't know if you know about the work by Jorge Pogo. He does reverse engineering visualization, and to do that, to train his machine learning model, he used CompassQL to generate a bunch of examples that he knows where it's from to. So that he can have a lot of training example to get basically like an OCR for visualization. So that's one application. I know that another friend at Georgia Tech tried to apply the same engine more for the national language UI for visualization.
It's sort of a program synthesis system in Alex terms, right? You have a partial program, partial specification, and then there's a system that fills in those holes to create these more detailed full Vega-Lite specifications, which then get compiled to Vega.
So if there are any other questions, I encourage you to come up and you can make some time to meet with these folks and talk to them. And let's thank our speakers.
Thank you.